You are welcome to the GMAETS 41's live class. Today we are going to be giving attention to physics in this particular live class. I know that some of us have been waiting and anticipating because the class was meant to have kicked off some minutes past, but all the same, you know, I am here now. The GMAETS 41, we are going to be giving attention to this topic in physics, basic electronics, semiconductors. That is what we are going to be studying in this class. Semiconductors, a topic that you need to also be prepared for as you get set for, you know, the JAM examination. Yeah, speaking to those that are preparing for their JAM next week, Friday. And of course, our white students. Okay, and it's also important for us to know that whether we are sitting for JAM or not, sitting for WIC or not, we need this topic. Yeah, it's possible that we are in advanced level. Depending on the course you do, you will be exposed to basic electronics, the concept of semiconductors. So once again, I want to say welcome to you, friends. Yeah, Basil, good evening. You're welcome to the class. Remember to share this the link to this video class to your friends, okay? Those who are sitting for this forthcoming examination, invite them to join this class. This class is a full-blown class on this topic that we are going to deal with. Is that okay? Because we're going to look at the topic step by step, after which we will consult certain questions, you know, exam-related questions. As you are highly likely to see in your forthcoming examination. So to start up with these semiconductors, I would like us to take our mind back to the concept of conductors. All right, in basic current electricity, we talk about conductors. And then I would like us to also take our mind back to insulators. Insulators. Conductors are materials that have high conductivity, so they allow current to flow through them easily. Which simply means that conductors, they have low resistance. Okay, they have low resistance value because they allow current to flow through them quite easily. Good example of conductors include metals. Metals like copper, silver, iron, aluminium. What about electrolytes? Electrolytes, where you talk about maybe copper 2 sulfate, where you talk about sodium hydroxide. These are conductors. Insulators. These materials, they do not allow current to flow through there. Yeah, generally speaking. Their level of conductivity is extremely low, which means they have high resistance. And that is why they do not conduct electricity much easily. Examples of insulators include glass, nylon, wood, okay, dried wood to be specific, mica. These are insulators. Now, try to understand what we've said here. These guys, they have high conductivity. High conductivity. All right, high conductivity, meaning that their resistance is low. Then this one has, these ones, they have low conductivity. In fact, let me specify very low. And then this one, very high. Between these two guys are materials that we call semiconductors, which means that the idea of semiconductors refer to materials that have conductivity values between conductors and what? Insulators. Semiconductors are materials that have conductivity values between conductors and what? Insulators. Remember, like I said, conductors, they allow current to flow through them easily. Insulators do not. Coming to semiconductors, there are certain conditions under which semiconductors will allow current to flow through them easily. And then there are certain conditions under which semiconductors will not allow current to flow. That is why we say that semiconductors, they have conductivity value between conductors and what? Insulators. Semiconductors. So their conductivity value is between that of conductors and that of insulators. What are some examples of semiconductors? I'd like to mention these ones, very important. Silicon, it's a good example. Germanium is another good example. Silicon and germanium are semiconductors we are going to give attention to in this class. All right? Like I said, remember that semiconductors, they have conductivity values between these two guys. Queen Jumia, you just came on and you just have question. That's not funny. Follow up with our classes if you're here to learn, okay? Your questions you can ask much more later, especially if it is not related to this topic. And if it is not related to what I have said so far, you can ask us questions ahead per se for now, even if it is in this topic. We are just kicking off the topic. All right, let us move on. Sophia, you're welcome to the class. Like I said, once you join, please like this video, like this lesson going on right away, give it thumbs up. Then share the links to your friends. Whomever you know that is preparing for this exam that is just in 6 days from now. You can do the person good by inviting the person to join the GMAETS 41's classes right away. We've been having these classes on and on and on. Perhaps some of you are just finding out. You may have missed some stuff, but no big deal. Any live class GMAETS 41 has, a copy of the lesson is always made available. So make good use of this channel. This channel is a wonderful one. There are academic wonders here in this channel. Go through our playlists. Go through the live session. You'll see video lessons as much as what you even need that can help you out. Blast your examination, your JAM, your WAEC. All right, we've talked about semiconductors, and like I said, these materials, they have conductivity value between conductors and what? Insulators. Under certain conditions, semiconductors will conduct electricity. And under some conditions, they will not conduct. So let us pick this semiconductor and then deal with it right now. I want to move on to the full, work of this topic. Having told you what semiconductors are and the two examples of semiconductors that this class is going to focus on, we would now like to give attention to the condition under which semiconductors will conduct electricity and conditions under which they will not conduct electricity. Normally, if you have a semiconductor, semiconductors exist in nature. Take note of that. They exist in nature with their electrons firmly held bound to the nucleus. Let's assume that this is an atom that is a semiconductor, say silicon or germanium. Silicon and germanium, they are tetravalent. They have 4 electrons in their outermost shell. So let us have 1, 2, 3, and 4. Let this represent the atom of either silicon or germanium. Now, in their lowest possible temperature, somebody may now ask, what is the lowest possible temperature of semiconductors? In lowest possible temperature, the lowest possible temperature of semiconductor is 0 Kelvin, which is equivalent to minus 273 degrees centigrade. 0 Kelvin or minus 273 degrees centigrade. They do not conduct electricity. in lowest possible temperature, in their lowest possible temperature, they do not conduct what? Electricity. So I can simply write they are non-conductors. They are non-conductors, which means that under this condition, they behave as what? Insulators. They behave as what? Insulators. Now, I have told you something very important, exam-related question. Under what conditions are semiconductors insulators? They are insulators in their lowest possible temperature, which is at 0 Kelvin or minus 273 degrees centigrade. Under this condition, they do not conduct electricity. And the reason is because their valence electron, look at these electrons, they are strongly held to the nucleus. They are held bound to the nucleus. They are not free to move. The question now is, what can you do to this guy so that it can now conduct electricity? So that the electrons will now be free to move. Because as long as the electrons are held bound to the nucleus, this guy wouldn't allow current to flow. But if you are able to free the electrons will now start to move, creating what we call holes in the study of basic electronics. As electrons move, a hole will be created, which is the vacant space from which the electron moved. Under what condition does that happen? In their room temperature, ordinary room temperature, in their ordinary room temperature, So someone might now ask, what is the ordinary room temperature of semiconductors? The ordinary room temperature of semiconductor is 0 degrees, which is equivalent to 273 Kelvin, not our normal ordinary temperature, ordinary room temperature. 273 Kelvin or 0 degrees centigrade. Now, please don't confuse this with this. For the Kelvin value, where semiconductors do not allow current to flow, they do not conduct electricity. For their Kelvin value, it is 0 Kelvin. When it's conducting, it is at ordinary room temperature, which is 273 Kelvin. In degrees Celsius, where it doesn't conduct electricity, it is minus 273 Kelvin. So a minus 273 degrees centigrade, because this is equivalent to 0 Kelvin. Then in degrees centigrade, where it allows current to flow, where it now changes or becomes a conductor, the degree centigrade value is 0 degrees centigrade. So under this condition, semiconductors will convert to conductors because they will now have good conductivity value. Under this condition, semiconductor will convert to insulators. At this point, the electrons are held bound to the nucleus. They are not free to move. Under these conditions, the electrons are now free. So we have what we call free electrons here. Free what? Electrons under these conditions. And so they can move. Here, no free electron. No free electron. No free electrons. Like I said, the electrons are held bound. Bracket, electrons are bound to the nucleus. Bound to the nucleus. Trying to squeeze up here. Good. So all these things are very important. I'm emphasizing on them because they are likely exam questions. If you're here to subscribe to this channel, please hit the subscription button right away. Don't waste time. And you can support this channel. You can support this channel by becoming a channel member on platinum level. That is 2,000 Naira Nigerian currency monthly. So you can just imagine, to be honest, that amount is not commensurate. It does not measure up with what the GMAETS 41 gives to you steadily. You yourself, you are aware of it. So please do support us. And you can also send GMAETS 41 super sticker, super chat right away as the class is going on. In the chat box there, you have the dollar icon by the right. If you tap on it, you would see the super stickers, you would see the super chat. You can support GMAETS 41 with whatever that is convenient for you. All right, guys, now that I have explained how semiconductors, the condition under which they act as conductors and the condition under which they act as insulators, we will now focus on what happens when they act as conductors, because that is the main thing we study in basic electronics. We are interested in seeing how we can convert these semiconductors to something that can conduct electricity. And semiconductors, they are very important, used in the field of communication, in the field of computer. Yes, the US, the Chinese, I think they manufacture these semiconductors a lot. In fact, it's one big thing that creates loghead between these two, tech giants, the US and the Chinese. So semiconductor is something very important. Now, we try to see how we can, make this guy to conduct electricity. Your computers, they are built, using this semiconductor stuff. In telecommunication, semiconductors, they are very much useful. Now, how exactly do they conduct electricity? What happens? Let us now look at this. I'm going to have these two diagrams. Let me assume that I refer to them as atoms. I hope that has not cut off. I hope you can view that. Okay, let me. Please check from that end if the network has been restored. This network these days, I just don't understand. Has the network been restored? This network issue, it's so annoying. Please check if the network has been restored. I'm sorry, the network just tripped off. Of course, you know where we find ourselves. I think the network seems to have been restored. Check. I hope the network has been restored at your end. Okay, OBDK, all good, right? Has the network been restored at your end? Whenever we want to move at the speed of light, sometimes in our classes, network will come with its problem. So annoying, don't you think so? Anyway, that is why you guys should always make use of our pre-recorded videos as well. It's just that I've not really made a video on semiconductors. That's why. Otherwise, I could have just directed you to go watch it. But all the same, the network is back. The network is back. Okay. So tell me, where did you stop in my explanation? Because this device I used to check what is happening at the end, I kept it because I needed to. It's moving at speed of. Is it up to speed of light? So tell me, what was the last thing when I was explaining this concept? The two things or the two charges that are created at agitation. Did you follow through? Or the network disturbed from here? Where exactly did the network start disturbing you? And I think I have to adjust the camera a bit, as if the left-hand side cut off. Let me adjust the camera a bit. Please tell me, where did the network cut you off from? Did you follow through when I explained this concept? The movement of electrons and the creation of holes. Indicate, please. Basil, you are there. Obidike, Chiagozie. Tell me, did you follow up when I explained how holes and free electrons are created? Did you follow up? If you follow up, please type yes. Let me know where the network disturbed from, please. I'm waiting for your response. Or is the network still disturbing you from your end? Okay. We stopped at when you drew 2 electrons, only just the circle. It seems the network, okay. So let's say I have to still explain this guy. I still have to explain it. I think I'll be checking at interval what is happening here. All right, let me hold this device. So this is what we have here. So that I've drawn all these things. This is an electron. Look at this, an electron. Is that okay? Oh, sorry. This circle represents an atom. I call the atom P. This one represents an atom. I call the atom Q. Then this blue shade of circle here, this one, and this one, they represent electrons. So I have 2 electrons. I just decided to use 2 electrons, okay? Then I said that when you heat these semiconductors, P and Q, they represent semiconductors. When you heat them by increasing their temperature, that process is known as agitation or excitation. You agitate them or you excite them by increasing temperature. Are you getting me right? Of the semiconductor. Something is going to happen here. This electron will be free to move. It will jump due to the increase in temperature. The electron from here, this E, I'm using the E to represent electron. The electron will jump from this atom P to a neighboring atom Q. When this electron is jumping, when it is moving, because it's now free to move, we call it free electron, due to the fact that you have increased the temperature. It will leave a gap here. That gap is the hole. It will leave a hole here. I decided to use black shade of marker to draw a big circle here to represent the hole. And I use H to label the hole. So this circle you are seeing here is the hole, which I use black shade of marker. I think the color is showing. If you are streaming at high resolution, you will see the color anyway. So this big hole, this big circle rather, represent the hole. And how is the hole created? When you heat a semiconductor, you excite it, you increase the temperature. The temperature either at ordinary room temperature or greater than it. The electrons will now be free to move. As the electron is jumping from atom P to Q, the neighboring atom, a hole will be created. In the same way, Q is also agitated. That hole is positive. That's what I use this key as a guideline. This circle with black shade here, which is hole, is positive. And then the electron, this one inside, the electron, is negative. So when the hole is created there because of this electron jumping to this neighboring atom, this electron in atom Q, in this semiconductor Q, because that Q is also excited, it's also agitated, the electron from here will jump also because it's also free to move. It will be attracted to the hole created from here, or created at this point. Are you following, right? So there is something that is happening here, a kind of movement like this. You agitate these 2 atoms, let's say they are semiconductors. The electrons will be free to move. As the electron of this guy is jumping to this place, it is creating a vacant space, which we call a hole. That hole is positive. So the electrons of this guy, being also agitated, will jump. And electrons are negative, so normally they will be attracted. Are you following, right? Naturally, using the fundamental law of charges. The electrons from here, as they are jumping, they will be attracted to the hole, which is positive here. Then remember, as the electron of this guy is jumping from here to the other guy, it's leaving a hole. So the electron coming from this atom now will now go and fill in the hole here. So there is this intermovement of electrons. And this happens when you agitate a semiconductor by increasing the temperature. The network is what again? Shagozi, what do you say? The network, what happened to it? But this device is moving well here. Okay, the network is back again. It's back, sir. Okay. I thought you said it's bad again. All right. Having explained this concept, I now wrote something here. At agitation or excitation or increasing temperature of semiconductor, the following are created. The following charges. There are two charges that are created there. One is negative, and the second is positive. The negative charge are called free electrons. Are called what? Free electrons. Then the second charge are called holes. The holes are positive. And these two guys are responsible for the conductivity of semiconductors. You must have positive and negative charges for there to be a level of current, a level of allowance of current flow. And this is how they are found. Now, what I wrote on top here, I wrote it to explain how temperature affects the resistance and conductivity of semiconductors. This R here represents resistance. T is temperature. This symbol here, I'm using it to represent conductivity. So you can see the relationship. For semiconductors, resistance is inversely proportional to temperature. But that is not true for conductors. Conductors, in the case of wires, you have something like copper, zinc, copper, silver, iron. For wires, right? If you increase their temperature in the case of conductors, resistance will increase. We studied that under current electricity. Increase in temperature increases resistance. Therefore, the conductivity of that material will reduce. That is for conductors. For semiconductors, the opposite is the case. If you increase temperature, resistance will reduce, which means that the conductivity will increase. Semiconductor conductivity is directly proportional to temperature. The higher the temperature, the higher the conductivity of a semiconductor. So that is it. And I think I am done explaining this concept here on the board. You can quickly put them down, screenshots. I've always advised that because there's no time, so that we can move on to the next item. I hope the network is no longer disturbing from your end. It is stable at my end. So finish up. All right. Trying to check what is happening at your end. I'm wiping this. We are now going to move on to types of semiconductor. Types of semiconductors and how they are formed. Before I move on to these types of semiconductors and how they are formed, I would like to emphasize that the two examples of semiconductors I gave, silicon and germanium, they are called pure semiconductors. Pure in the sense that the number of electrons and the number of protons they have are equal. In their lowest possible temperature state, which is 0 Kelvin, the number of protons and the number of electrons, they are equal. Right? Even when you increase their temperature and there is this flow of electrons and stuff like that, they are still equal. So they are known as pure semiconductors. You can make them to become impure semiconductors, and that is what leads to the types of semiconductors that we have. So I want to take note of that. We are going to talk about types of semiconductors now. And there is something I want to say here quickly also. This movement of electrons and creation of holes, okay? In this state, the electrons, they move anyhow. They move anyhow. Now, when you apply a potential difference across this, if you apply a potential difference across this, that is connecting it to maybe a cell, a battery. Let's assume I have something like this. You know, you now connect to say a battery. Now the electrons will now be given a directional movement. They'll be giving what? A directional movement. Here is positive, here is negative. Electrons will start moving towards the positive like this. Electrons will start moving towards the positive, something like this. Electrons will be moving this way, from the negative to the positive. That is to say, these guys, the direction of movement of the electron will no longer be random. Rather, it will be given a particular direction as a result of connecting it to a given potential difference. Now, as the electrons are moving from the negative terminal to the positive terminal, inversely, current will be moving the other way around. Current will be moving from the positive to the negative. And that is how this guy is used to, you know, conduct electricity, semiconductors, okay? That's how they are used to conduct electricity. Okay, so having said this, that if you apply a potential difference across this, the electrons will be given a specific direction of movement. And I've told you, they will move from the negative terminal to the positive terminal. And then in the opposite side, current will flow. We now want to look at types of semiconductors. Remember, I told you that these types of semiconductors, they are formed and referred to as impure semiconductors. And don't forget, the pure semiconductors, silicon and germanium, in their pure state, they have 4 valence electrons. There is something that can be done to them in order to make them impure, which gives rise to our types of semiconductors. So I have these types of semiconductors. Types of semiconductors. You know, the reason I took my time to explain all these concepts, rather than just mentioning, defining, stating, and then we are moving on. The reason I took my time to explain this is to ensure that you follow through and understand this for what they are, not just to start cramming stuff to go to exam hall and write. You would understand, you know, how to attempt your questions, no matter how the examiner presents it. So I had to take my time to explain this concept, of course, as usual, of GMAETS 41. So let us look at the types of semiconductors. There are 2 main types. We have the P-type semiconductor. P-type semiconductor. And then, of course, if we have the P-type, that P there means positive type. Positive type. And then we have N-type. That N-type means negative type semiconductor. Negative type semiconductors. These are the 2 major types of semiconductors. I hope the network is not disturbing. That's good. We are there. Gift, you're welcome. From Donatus, you're welcome. Remember, as you are joining the class, right away, just be sharing the link to your friends. Invite them to join the class. Now let us move on. These are the 2 types of semiconductors. Take note of that. Now, examiner wants you to know, and of course you should know, imagine you're working in basic electronic company. You should know how these types of semiconductors are formed. How are they formed? The P-type and the N-type. This will now take us to a process known as doping. A process known as what? Doping. We are going to define the term doping. Because it is through the doping process that you convert pure semiconductors to impure semiconductors. Take note, these P-type semiconductors, N-type semiconductors, they are impure semiconductors. The formation of this P-type and N-type, there is something you did to form them. And that thing you did, the process is called doping. In doping, what you do is to introduce impurities to pure semiconductors. So let us define doping before we explain how P-type and N-type semiconductors are formed. I hope the network is moving okay. That's good. No interference. And I just pray and hope that the network doesn't disturb any further. Doping. Doping is defined as the process of introducing a foreign element or impurities into a pure semiconductor in order to convert them to impure semiconductor, either by increasing their numbers of electrons or reducing their numbers of electrons. I'm going to write the definition on the board. This is the process of introducing or adding a foreign element or impurities into a pure semiconductor, in order to increase or decrease the number of electrons in the semiconductor. So this is what doping is. Remember, the aim of doping a pure semiconductor is either to increase or reduce the valence electron of that pure semiconductor. And when this is being done, any one of these guys will be formed. When it is done, any one of these two guys will be what? Formed. So you want to take note of that. So at this point, having known what doping is all about, we are now going to learn how these types of semiconductors are formed. Please finish up what is on the board. Okay, finish up what is on the board. I'm going to wipe this part. I hope you are done with it. Okay. All right, so let me wipe this part now so we can talk more about the formation of P-type and N-type. Now, before we move on to the formation of this P-type and N-type, for you to understand the concept properly, we are going to first talk about materials that are used to dope a pure semiconductor. I repeat, materials that are used to do what? Dope a pure semiconductors. So I'm going to have doping materials. You are expected to bear this in mind as you prepare for your exam. Doping materials. Now I'm going to itemize them. I'm going to mention them in order. Please, the order I'm going to give you these doping materials, make sure you follow through. Don't just learn them in a scattered way. It's going to help you if you follow this order. Now, the first thing I'm going to give will be that of indium and boron. Let's see, because I want to take these two types, one in order, P-type and then N-type. So I'm going to give you doping materials. One, let's say 1A, indium, In. Indium, In. That's the symbol for indium as an element. Indium is an element. Why not find the atomic number of indium? Find the atomic number of indium, although that is not really of importance in this topic. But I'd like you to know the valence electron of indium. I'll tell you, but you can still go ahead and find out. Then 1B, boron. Using the knowledge of boron, at least you can get to know the valence electron of indium, because indium and boron, they have the same valence electron basically, and we know that boron has 3 electrons in the outermost shell. So indium and boron are trivalent. They are what? Trivalent. These are trivalent. These are trivalent. You use them to dope. And whenever you use them to dope a pure semiconductor, pure germanium, or pure silicon, you expect to get a P-type. I'm going to tell you how that happens. Now this will take us to 2. Doping materials. 2A. We have arsenic. Arsenic. AR. And we have 2B, antimony. Antimony. SB. Antimony SB, I think they use the Latin name to give the symbol. This is it cibitium or something. Cibitium, yeah, the Latin name of antimony. Guess right, yeah, that's cibitium. So you can go and find out all of those things. These are generally pentavalent. Pentavalent. These are pentavalent. So these 4 guys, you want to take note of them. They are doping material. All right. Network is not disturbing, so we are moving. You know, at regular interval, I'll be checking so as to be sure that we are free from network problem. So these are trivalent materials, you know, meaning that they have 3 electrons in the outermost shell, right? And then this doping material, arsenic and antimony, they are pentavalent, meaning they have 5 electrons in the outermost shell. If you dope a pure semiconductor with arsenic or antimony, you are expected to get N-type semiconductor. And this is not what I just want you to cram. No, I know that as you're going for your exam, you want to have that in mind, but try to understand these, because the knowledge of chemistry can really help us to know why indium and boron, which are trivalent, when used as a doping material, why they produce P-type semiconductor. And then why arsenic and antimony, if you use them to dope a pure semiconductor, why they will give you N-type. You should understand that. And the trick is as simple as this. We want to compare this with compare these guys, this doping material, with our semiconductors. Our pure semiconductors are germanium. Germanium is Ge. And then silicon. Yeah, silicon. In their normal state, they are pure. They are pure because the number of electrons and protons are the same. Is that okay? These guys are tetravalent. They are what I said. These semiconductors. Semiconductors generally anyway are tetravalent because these guys are group 4 elements. Group 4 elements in chemistry. But then we are specific about silicon and germanium. They are the ones used as semiconductors. These semiconductors are tetravalent. You know, they are in the same group as carbon. They are in the same group as what? Carbon. They are tetravalent. In their pure state, they are tetravalent. In their ground state, they are tetravalent. Now compare these semiconductors, which are pure, with these doping materials that are trivalent and these doping materials that are what? Pentavalent. If I compare this guy, pure semiconductors, with trivalent, indium and boron, you will agree with me that the number of electrons in these pure semiconductors are greater than the number of electrons in these trivalent doping materials. So what happens? Let me assume that this is germanium now, pure germanium. Number of electrons and protons are the same. And now I decide to dope this guy by adding a doping material to it, by introducing a doping material to it. Am I communicating? Let me get another pen so that you can follow through. Let me assume that this is the doping material and that this guy is trivalent. So it is either boron or indium. By the time you introduce it into this semiconductor, what is going to happen? The semiconductor has excess electrons. Yeah, compared to this. Semiconductor has excess electrons compared to this indium or boron. Boron is trivalent. The semiconductor is tetravalent. Either the boron or indium is trivalent. So since the semiconductor is tetravalent, we say that the semiconductor has more electrons. So what is going to happen? These semiconductors will now donate electrons. We give electrons. That's what happens here. Please take note. It is not this stuff you learn in chemistry where you say the one that has, lower valence electron will give electrons to the one that has higher valence electron. That is not what happened in semiconductors. In semiconductors, the one with higher number of electrons will give electrons to the one with lower number of electrons. Now the semiconductor in its pure state, like I said, germanium, silicon, they have 4 electrons in their pure state. They are pure semiconductors. So if you are now doping with a trivalent material, indium or boron, which is trivalent, the semiconductor will lose electron, will give electron to the trivalent material. So what is now be the resulting effect on the semiconductor? The number of electrons will now reduce. The number of electrons will now do what? Reduce in the semiconductors. Which means you will have more positive charges per se in the semiconductors than the number of electrons. Understand this. This semiconductor being tetravalent will give electron to this doping material which is trivalent. Because this guy has fewer electrons. The one that has higher electrons, okay, let me help you. Or you take. So the pure semiconductor will give electron to this doping material that is trivalent. Now the result to this semiconductor will be that this semiconductor will now have less electrons compared to, supposedly if you want to mention, say, protons, at least for the idea to be clear. It will have more electrons compared to what? The protons. Which means there will be greater, higher protons here than the electrons. But mind you, here we don't use the term protons. The positive charges, we use hole for it. Because the electrons have moved. Now, the electrons have moved, rather. The electrons have moved. A hole is now created. So this guy will have more holes, more positive charges than negative charges, than electrons. So anytime you are doping a pure semiconductor with a trivalent material, what is expected is that the pure semiconductors will lose electron, thereby having more holes than more electrons. And when you have more holes, it means you have more positive than negative. In that case, since that semiconductor now has more positive charges, it will now be what? P-type semiconductor. Because you have more positive type. And that is how these P-type semiconductors are formed. They are formed as a result of doping a pure semiconductor with a trivalent material, indium or boron. And of course, like I explained, in the process, the semiconductor will lose electron, give electron to the doping material, to the trivalent material, thereby leaving the semiconductor with more holes, positive, P-type, than the electrons. So that is what or how P-type semiconductors are formed. That takes us to N-type semiconductors. Back to this guy again. It takes us to N-type semiconductors. Back to this guy. This is our pure semiconductor, tetravalent. You want to form N-type semiconductor. These are the guys you use to form N-type semiconductor, arsenic and antimony. Any one of them. So let me take this blue marker to be the antimony or the arsenic. When you dope this semiconductor, which is pure, tetravalent, with this doping material that is pentavalent, 5 electrons in the outermost shell, antimony or what? Arsenic. You introduce this foreign element now. This impurity, you introduce it here. This pentavalent material, you introduce it here. This antimony or arsenic, you introduce it into this semiconductor. Remember what I told you when I explained the formation of P-type. Because arsenic or antimony is pentavalent, it has more number of electrons than the pure semiconductor. So what this pentavalent doping material will do is to give lose electron to this semiconductor. What will now be the effect on this semiconductor? Remember, this pentavalent material, arsenic or antimony, has more electron. So has more electron compared to the semiconductor. So it will now lose electron to that semiconductor. The semiconductor will now gain the electron, thereby having more negative charges than the positive charge. And of course, when this guy has more negative charge than the positive charge, the negative charges are the free electrons. The positive charges are the holes. And we are saying that in doping this semiconductor with the pentavalent material, this guy will gain electrons. Therefore, you have excess negative charge than what? The positive charge. And because you have excess negative charge in this case, this semiconductor, which has been doped with a pentavalent material, being that it has excess negative charge, it will now form what is called N-type semiconductors. It will now form what we call what? N-type semiconductors. So that is just the whole idea. And that is why I told you, the way I give you these doping materials, please bear them in mind. Yeah, memorize them in mind in this order. Indium and boron are trivalent. As doping material, if you use them to dope a pure semiconductor, they will collect electrons from that semiconductor, meaning that the semiconductor will lose electrons to them. And if the semiconductor loses electron to them, what is going to happen? This guy will now have more holes, more positive charges than negative charges, thereby becoming a p-type. Arsenic and antimony are pentavalent doping materials. When you use them to dope a pure semiconductor, germanium or silicon in its pure state, they are pentavalent. They have more electrons than the what? Than the semiconductor that is tetravalent. So, this guy that have more electrons will now give electron to the what? The semiconductor, which means that the semiconductor will gain electron when you dope them with this pentavalent material. The result, more electrons, more free electrons in the semiconductors, which are negative compared to the holes. And because you have more negative in the case of doping this guy with pentavalent, this arsenic and antimony leads to the formation of N-type semiconductors. So, is carbon among, since it is also tetravalent? No. Carbon is not used as a semiconductor. Okay? You know, carbon on its own form one other part. God has created this in nature. They have their own work they do, right? The parts they play. You know, you study carbon in organic chemistry, where you use them to produce most of all these materials around us, right? Plastics, can mention them, what have you. So carbon is not among semiconductors, please take note, even though it is in group 4. All right, finish up what is on the board before I wipe. But before I wipe this, I'm going to ask you this question. In P-type semiconductors, what do we have more there? Holes or electrons. In P-type semiconductors, what do we have more in that P-type semiconductors? Do we have more holes or more electrons? What do you have to say? Does anyone have any response to that based on what I've just explained? Based on what I've just explained. P-type semiconductors. Do we have more holes here or more electrons, more free electrons? What do you have to say? Good. Frank Donatus, more holes for P-type. You are blessed. N-type semiconductors. Do we have more holes or more free electrons? Do we have more holes or more free electrons? There's a reason I'm asking you these questions, and these are exam questions. I'll tell you when you are done giving me this answer. Yes, what do you have to say? Ochiko, in P-type semiconductors, we have more holes than electrons. That's correct. It's in line with what Frank Donatus also said. So what about N-type? In N-type, do we have more holes than electrons or more free electrons than holes in N-type? That negative type semiconductor, yes. What's your response? Electrical. In N-type, we have more electron than holes. That's correct. Frank Donatus, that's correct. We have more free electrons for N-type than holes. That's good. Do you know why I asked this question? Examiners, you're preparing for your jam next week. We are just very close. I think it's on Friday, 25th. It will start. And then those preparing for WAEC. If you're in advanced level, maybe if you're in electrical electronics engineering, or you're studying computer science and the rest, you will be exposed to basic electronics as well too. So you need to have all these things in mind. And this is the startup. If you don't understand this at that level, you might be finding them difficult. You might be asked, what are the majority career? In one of my short video on this channel, I think that was yesterday or 2 days ago, I asked a certain question in that short video, all right? And then I asked, what are the majority career and what are the minority career in P-type and N-type semiconductors? So your examiner can ask you that question as you're preparing for exams. In P-type semiconductors, the majority career are the holes, because you have more positive there. More holes. So the majority career in P-type are the what? Holes. So I've answered that question that I asked in that short video. If you go to the GMAETS 41 short, all right, in our homepage, you know, if you get to this particular channel, all right, if you get to the home, you have videos, shorts, lives, playlists. If you go to the shorts, you see where I ask these questions. In P-type, the majority career are the what? Holes. And the minority career are the electrons, the free electrons. In N-type semiconductors, the majority carriers are the free electrons, or simply the electrons. While the minority carrier in N-type are the what? Holes. Because there you have more electrons than holes. And these are important because it is the interplay of holes and electrons that leads to the conductivity of these semiconductors. Now take note that these semiconductors, P-type and N-type, they are impure semiconductors. Pure semiconductors is when you have not doped them. In this case of P-type, you have a doping material inside. And the doping material inside this guy, it's still germanium or silicon, but not pure germanium, not pure silicon. In the P-type, you have either indium or boron inside this germanium or silicon. And then in the N-type, this is also impure semiconductor. You have either arsenic or antimony inside this germanium or silicon. So these guys, they are impure semiconductors. Take note. Hello, sir. I am listening from the United Kingdom. Edward, thank you very much for connecting to this class. You are welcome, and I hope you learned something from this class. Definitely, you are going to learn. Okay? You're highly welcome to join us in Nigeria here. You have your Nigerian friends here. You know, technology has made this world a global village, and so we can link up anytime, any day. Let us move on now. Having explained the formation of P-type semiconductor, N-type semiconductor, the one that, you know, has holes as majority carrier, the one that has electrons as majority carrier, and then of course there are minority carrier stuff. So finish up what you have on the board. You can screenshot in order to be fast, so that I will wipe what is on the board. Tejas, you asked the question, is hole just absence of electrons? Is holes just absence of electrons? Well, I would say yes to that, but not entirely yes. Anyway, I think I'm trying to figure out actually what you are pointing to in asking that question. What made you ask the question? When there is no hole, it means you have electron, not true. When there is no electron, it means you have hole. However, that you have hole does not mean that that guy does not have electron at all. Holes and electrons, they are found as mixed up in a particular atom that is a semiconductor. But the only thing is that if an electron moves, as it is moving, the space where that electron leaves, a hole is created. It does not mean that you don't have other electrons there. You have. Think, for example, in the case of silicon, germanium, they have 4 electrons in the outermost shell, tetravalent. Imagine that I have this. And then you have 1, 2, 3, and 4. Let us assume that this guy moves. If it moves, I'm going to wipe the electron from here. Because that electron moved. It is not existing somewhere here, maybe in a neighboring atom. It has created a hole here. It has created a hole, a vacant space. So if that is what you mean, then yes to your question. Holes means absence of electron. However, it doesn't mean that once you have hole, then there is no electron around again at all. That is not what it means. Like in this case, you still have electrons there. Okay, you still have electrons there. But you have a hole created. So I hope I'm able to answer your question, except if you have another reason why you asked the question, you can indicate. And then, mind you also, if you have more electrons in something, even if no electron left there, if you have more electrons in that thing, are you following? Like in this case, let's say that I've got this. Let's say I've got this. And then you have 4 electrons as usual. 1, 2, 3, 4. This is tetravalent. If you go to the study of chemistry, you know the concept of forming octet structure. This guy normally, to complete its outermost shell, it needs how many electrons? It needs 4 more electrons. Let us assume now that other electrons, during the doping process, this guy received electrons. If he received electrons, let's say 1 electron, the fact that there is an increase in the number of electrons, it is now interpreted to mean that you have more electrons than what? Hole. Why did I say so? On a normal, let us assume that with this guy having 4 valence electrons, it still have 4 more spaces to be completed in order to attain the octet structure. 1, 2, 3, and maybe this 4th space. But that 4th space, something has entered. So here is no longer vacant, it's no longer open. So you now notice you have 1, 2, 3, 4, 5 electrons. And then how many holes? 1, 2, 3 holes. Initially, when this electron was not there, that is when you have not doped, we can say that you have 4 electrons and 4 holes, because there are 4 more spaces for this guy, to have a completely filled outermost shell. Now, it gained electron perhaps by doping it with a pentavalent material. That pentavalent material can only give it 1 electron. Am I communicating? To give you, okay, let's say 1 electron. Look at it. So that makes it possible that this guy has 5 electrons, and then the number of holes, instead of being 4, has now reduced to how many? 3. And that is, like in this case now, it's something like N-type, because you have more electrons negative, and then the holes have reduced. Now, in this case, look at this case. You have this vacant space. Remember, originally you have electron here. Let me fill it up. Originally, you have electron there. You have electron there originally. In this pure state, you have 1, 2, 3, 4 holes. Now, if you dope this guy with a trivalent, this one I explained is doping with pentavalent. If you dope this pure semiconductor with a trivalent substance, what is now going to happen? This will lose electron. We have to donate electron to that trivalent doping material. So let me say it gives this out. It gives it out. That will now create an extra space here. Let me wipe it. Let me wipe it. Create an extra space. Now permit me to put a cross there. So you can see that an added hole has been formed. 1, 2, 3, 4, 5 holes compared to 1, 2, 3 electrons. So this guy has more holes, making it P-type, because you doped it with a trivalent material, making it to lose electron. So that's just the whole concept here, okay? Frank Donatus, so this example made me understand this P&N-Type semiconductor very well. Thank you very much for the appreciation and, of course, commendation. You're welcome. That's what GMAETS 41 stands for. I'll continue to do my best to break this concept your friends are studying, to make this quite simple and easy as you go to your schools and other things. GMAETS 41 actually is creating and running something that seems to be an online school. So you guys should always tune in. Share the link to this channel. Share our videos to your friends. Encourage them to come. I'm committed to the process. That's it. There are no two ways about it. Breaking down this concept and making you understand them very well. Please finish up with what you have on the board. I'm going to wipe it now. Okay? I'm going to wipe it so that we'll be fast to round off. We would consider some questions. So it's important we round off. I want to believe you have screenshotted the stuff or you are done copying it. All right, so where do I wipe from? Here. We are done with the concept of types of semiconductors, where we have P-type and N-type. We've explained how doping process leads to the formation of P and N-type semiconductors. I've told you the importance of memorizing these doping materials. Indium and boron, they are trivalent and produce P-type. Then arsenic and antimony are pentavalent doping materials and therefore produce N-type semiconductors. We've explained that of these two guys, P-type impure semiconductors, N-type impure semiconductors. We've explained the one that has majority carrier and minority carrier, either as hole or electrons. We explained that P-type, the majority carrier that are responsible for conduction there are the holes, the positive guys. Why the minority carrier there are the electrons. Then if you now come to N-type, the majority carrier are the electrons, and then the minority carriers are the what? The holes. Having explained this, we are going to move on to P-N junction at this point. P-N junction. Because this guy he can behave, he can do the work of a thermionic junction, right? Thermionic diode rather. This guy can do, the same work that thermionic diode does. We can call this P-N junction a P-N junction diode. You can call it that. It is also a diode. It is a diode. And it does not respect Ohm's law. It doesn't respect Ohm's law. In our previous class under current electricity, I think I made reference to ohmic and non-ohmic materials. This P-N junction diode, just like thermionic diode, just like rectifier, just like thermistor, just like transistor, they are non-ohmic material. You can find out, what all these guys are. Google them. I cannot show you, a picture of them right now since I am on live for now. If it is a pre-recorded video, I could have showed you something. But for thermionic diode, it's just like you have a glass tube and then inside it allows current to flow in one direction. Yeah. Okay, just like a bulb, then that's filament in it and other things. So this guy can serve that function also, and hence we can call it P-N junction diode. So we start first by asking this question: how is a P-N junction diode formed? How is a P-N junction diode formed? A P-N junction diode is formed when a P-type semiconductor is joined to an N-type semiconductor. A P-type semiconductor is joined to what? An N-type semiconductor. That gives you the P-N junction diode. Let me assume that I use this to represent the P-type semiconductor. P-type semiconductor. And I'm using this black shade to represent N-type semiconductor. So this is P, this is N, P-N. Now you notice that here there is a thin connection between them, right? Connection between these two guys. And that is the junction where the P and the N-type meet. That is the junction where the P-type semiconductor and the N-type semiconductor meet. Frank Donatus, please, towards the end of the class, could you please show us the graph of non-ohmic conductor with respect to temperature? Yes, it's nothing difficult. Non-ohmic, the guy can go this way. It's a curve, not a straight line. Sometimes you could have, although this is voltage against current curve, and you could have something like this also. This is how the curve looks like. Is that okay? So no need of wasting time on it. You can see non-ohmic conductor, a curve. If you plot voltage against current, is that okay? So you're going to get a curve like something. If you plot against temperature, it's still the same thing. Do you get that? Unlike Ohm's law, Ohm's graph is a straight line like this. So that's what differentiates ohmic graph and non-ohmic graph. These two, they represent non-ohmic graph. All right, let us move on. I have told you how a P-N junction is formed. When P-type semiconductor is joined to N-type what? Semiconductor. To join them, of course, there are industrial processes that are followed to do that. Okay, so I've explained how this guy is formed. What is the symbol of this P-N junction? What is the symbol? Now, the symbol is this. The P-N junction symbol, let me draw it very big for you to see. Have something here like this. P-N junction. So if you think this is too big, it's too big. I think I can reduce it. So if you see this diagram, it represents a P-N junction. So this is the symbol for P-N junction, okay? That's the symbol. Please, sir, say hello to my brother Mike Oslang. All right, Mike Oslang, hello. I hope you're good, right? Hans Schittler, I've done so. I hope I fulfilled your request. Okay, guys, let us move on. When talking about this P-N junction, I've told you that this guy can serve the function of a thermionic diode, which allows current to flow in one direction. Because this guy can allow current to flow in one direction, it can. Okay? And that's what it does. It allows current to flow in one direction. But the question now is, what can we do, or what do we do to a P-N junction in order to make this happen? This is also a type of semiconductor anyway. P-N junction, that is a type of semiconductor. However, we don't classify it as major type of semiconductor, just like we have P-type and N-type. Okay, so you have this in mind. If you ask type of semiconductors, it's P and N-type. But this P-N is also a type, in case you hear. However, we don't classify it as major type. It's on its own. Now, I want to find out what you can do to this P-N junction, diode, in order to, make it conduct current. This will require that you connect a potential difference across its terminal. This is the positive terminal, Of course, you can see it with P. That's the positive terminal. And then this is the negative terminal. This is the negative terminal. So let us see what happens. We are going to study the forward biased connection of this PN junction and the reversed biased. Under what connection of potential difference do you refer to this PN junction diode as a forward biased PN junction diode? And under what condition do you refer to it as a reversed biased PN junction diode? So that will take us to forward biased. Forward biased PN junction. PN junction. Now, for you to refer to this PN junction as being in forward biased, you are going to connect a potential difference across its terminal, connect the terminal, to a cell, and connect them accordingly. What do I mean by connect them accordingly? The positive terminal is the P-type will be connected to the positive terminal of the cell, and the N-type will be connected to the negative terminal of your cell. So we have something like this. So have something like this. Under this condition, you refer to the connection as forward biased. You refer to it as forward biased. So I am connecting it now. So this is going to be, this is P and this is what? N. Trying to use different shades of marker so you can follow through. So it goes this way. And then for the positive, we have this. Negative terminal of a cell, we use a shorter line for it. So this is positive plus. And this is what? Negative. So look at what happened in this forward bias. For a PN junction to be connected in such a way that you refer to it as forward biased, the P-type will be connected to the positive terminal of the cell, while the N-type will be connected to the negative terminal of the cell. Now look at what happens. In this case, you would have, in P-type, the majority carrier is what we said. Holes. Holes are the majority carrier. So here we have positive terminal. Let me use circle to represent holes. And then let me use E to represent electrons, okay? So normally, this positive, because it is connected to this positive terminal of the cell, because it is connected to the positive terminal of the cell, there is going to be repulsion. There's going to be what? Repulsion. Yeah. This is positive. Observe what is happening here. The P-type has more positive. And here is also what? Positive. Positive terminal of the cell. So there is going to be a repulsion here. Repulsion. So let me just write repel. Which means that the positive charges will be repelled, pushed away. When they are trying to come this way, the potential difference you applied, the positive terminal from that cell will push the holes. And once they push the hole is going to cross this junction. The hole will be moving this way, like this. And then they are attracted to the negative terminal. And normally for conduction of electricity, it is expected that positive will be attracted to what? Negative. That's the normal thing that happens. So in this connection, where you connect positive to positive, there will be repulsion of the holes here. The same thing happening here. These electrons from the negative type are connected to the electrons here. So at this point you have negative from the cell, and here you have negative from the N type. So there is going to be repulsion here as well to repel, which means that the electrons from that N-type semiconductors will be repelled by this negative terminal of the cell. repel, push this way. So the electrons will now be moving this way. And as they move that way, electrons will now be attracted to the positive terminal, which is what is expected, like I said, for conduction. For electrical conductivity, the electrons are meant to be moved to the what? Positive terminal. And then current will now flow in the reverse process. So this thing that happened where electrons are now moving towards the negative terminal. So no, electrons are moving towards the positive terminals, and positive charges, are moving towards the negative terminal, will now allow current to flow. It will allow a very large current. So let me label here as I, which is current. Current will now be flowing. So what is the idea? In this connection, which is called forward bias, whereby you connect P-type, in the P-N junction, you connect P-end to the positive terminal of the cell and connect the N-type to the negative terminal of the cell. This arrangement is called forward biased arrangement. And in this case, large current will flow. Large current flows. I think this is as if this has cut off from view. Let me adjust the camera. Let me adjust the camera. Go back more. All right, that's good. Chico, you asked the question, so please, sir, would there be recording of this video? Yes. All the GMAETS for the ones live classes are being recorded, and just after the class, it will be automatically uploaded. You just wait for release and you will see it there, okay? So if you go in the home page of this channel where you have home, videos, shorts, live, playlist, membership, posts, click on that live. You'll see this particular video and even many more that you may have missed. Large current flows in forward bias. Flows in forward bias. In forward bias arrangement. Forward bias arrangement. So you want to take note of this. Okay, then the next one is reverse bias. Reverse biased. P&N junction diode. Junction diode. The reverse bias is just opposite of this. It's just opposite. So I don't want to talk much about it. Right? What will happen now is to reverse the connection. That's just what you do in reverse bias. So if I am to draw again, I'll have something like this. Something like this. This is the P. And then connect this. Connect this to our cell. So all you have to do is to reverse. Remember, this is your P. And this is your what? N. So reverse the terminals of this cell, which means that negative will now come here, while positive will come here. This is too fast, so let me bring it close. While positive will now come here. So this is positive, and then this is negative. So you see, you reverse the arrangement. You reverse the arrangement of the cell. Positive terminal of the cell will be connected to the negative type semiconductor. The negative terminal of the cell will be connected to the positive side. Now notice what is going to happen in this case. You notice that you have excess hole. Majority carrier, the holes in the P-type. And here is negative end of the cell. So there's going to be attraction. There's going to be what I said, attraction. The holes, the positive charges here will be attracted to this negative. And then here, the negative will be attracted to this positive. Creating no flow, no good charge flow across the junction. Here there is a good charge flow across the junction. You know, the positive are going this way, the negative are going this way. Here, there will be no clear charge flow across the junction. And when there is no flow of charges across this junction, then it means that this guy will not produce much current. In this reverse bias, the current that is produced here will be very low. Do you understand that? Because nothing is crossing here. Look at it. Holes, which are positive, electrons. This will be going this way. The electrons will be flowing this way. The holes will be flowing this way. And you see, holes are positive. This is negative terminal. So there is going to be, at this end, we have positive here. Positive and negative. So what happens here is attraction. Attraction. And then here, we have negative. While the terminal of the cell is positive, once again, there's going to be attraction. Attraction. So like I said, as this guy moves this way, there will be no charge flow across the junction. So permit me to put a cross here, okay, like trying to cancel it. The cancellation means no full charge flow across this junction. And whereby there is no full charge flow, whereas charges are not crossing this junction. If opposite charges are not crossing this junction, it means that this will not conduct electricity. It won't allow enough current to flow. So I would write here that small current flows across the junction in this reverse biased arrangement. So this is what you should know about PN junction when it comes to your preparing for exam. Are you following, right? Yeah, this reversed and forward biased. You want to give attention to them, and then of course with this knowledge we can now talk about the use of PN junction as a rectifier. The use of PN junction as what? A rectifier. And because it can be used as a rectifier, you convert this guy to, you can use a PN junction diode to convert alternating currents to direct current. You can do that. Because if you look at this, current can only flow in one direction as it is. Finish up this, please. I want to sketch the graph of this thing for you. Two of them. So finish up what you have there on the board, so I can wipe off, and we just do a round off. We are 1 hour 37 minutes gone. And I hope that you are learning. I hope you are learning. I'm going to wipe this. So I will sketch the graph. Just a single graph showing the flow of current. Remember, large currents here. This place you have small currents. The graph of this current flow in this PN junction connected in this forward and backward, forward and reverse biased. Okay, the graph, if you plot voltage against current, you're going to get a graph that goes this way, something of this kind. So here, this part shows forward bias. From the origin, you go this way, forward biased. And like we said, you have large current flowing here, large current, because charges will be crossing that junction. Then this side you have the negative. You know, these are positive voltage, positive currents. Here is negative voltage, negative V, and then negative I. The negative part. This is the origin 0. This is reverse bias arrangement. Reverse biased. So I'm going to write it reverse biased. That's reverse bias setup. The graph goes down. Are you following? And like I said rightly here, small current is obtained here. Small current. In this case, the PN junction diode will just be producing small current. If you are to fix a milliammeter here, if you are to fix a milliammeter here, a milliammeter is also a device used to measure small current. If you fix a milliammeter in this case, maybe please permit me to draw something here. The milliammeter will face this direction. But here, in this case, the milliammeter, if you fix it here, to be facing this direction, a large deflection. The pointer of that milliammeter will deflect very large, showing that more current is flowing here. But here in the reverse case, the current will be going the other way, right? It will be going anti-clockwise because you reversed the connection here. Is that okay? And then the deflection of the milliammeter will just be something small in the anti-clockwise direction. Why in this case it will move clockwise with large deflection. Is that okay? So this is the graph, please. Take note of that. Finish up this, right? Okay, I think I can write what I want to write below. Notes. PN junction diode is used as a rectifier. It can be used as a rectifier. And what does a rectifier do? A rectifier converts alternating current, AC current, that's AC, to direct current, DC. Is that okay? I hope the network is not disturbing. All right, we are there. Everything is working for good. I've got a question here. Sir, please, will this video be available? Yes, I've said that it will be available. Tejas, you have a question. Are holes just absence of electrons? I thought I've answered this question before. I've answered it before. Okay. So like I said, this guy can be used as a rectifier. I want to take note of that. PN junction diode can be used as a rectifier. And what does the rectifier do? Because that's the same thing that the PN junction will now do as a rectifier to convert AC, alternating current, to direct current, DC. We are coming to a close of what you should know. Remember, when I started this class, I told you it's going to be a full-blown class. It's going to be a full-blown class. Yes, start and finish. And not just a class to come and just talk. It now. Crystal clear explanation, like, of course, you guys would have seen. Okay? What you do in the case of rectifier, you just connect the PN junction to that alternating current. If the alternating current is coming like this, are you following right? Maybe it's like alternating current move now, something like this. Along that path of that alternating current, connect, because you have something like a wire. You have something like what? A wire. Let me demonstrate it here. Imagine you have an alternating current through this, say a conductor is coming this way, alternating current, it alternates, sinusoidal, the graph of sine. Okay, now along the path, connect a PN junction diode there. So as the current is coming, the alternating current is coming. Once it passes through this PN junction will now convert it to direct current. To no longer be moving this way, to just be a current that moves, directly. So that is it. And so I think we've done some good works on this. I said we were going to solve some questions. Meanwhile, some advantages of PN junction, you are expected to know that. Some advantage of PN junction diode. Okay, you're expected to know that. And don't forget, I've told you that PN junction diode is a non-ohmic material. I think I mentioned that earlier. So what are some examples, some advantages of this PN junction diode? It is small to carry. Okay, it is small to carry if you compare it to thermionic diode. These advantages we are checking, we are trying to compare it to thermionic diode. PN junction diode is small to carry. That's one good advantage of it over that guy. All right. And of course, the potential difference it needs to operate it. Like I connected this thing here, the potential difference that PN junction needs to operate it compared to thermionic diode. The potential difference required by PN junction is small. It doesn't require much voltage value. Are you following, right? Potential difference value to operate it. So because it requires, you know, a small value compared to thermionic diode, that makes it more useful and advantageous than thermionic diode. Another advantage is that your PN junction diode does not require time to warm up. It doesn't. It doesn't require time to warm up so that the electrons and holes will not be of current to flow. Already inside that PN junction diode, you have free electrons and you have holes, so they are free to move anytime. So the fact that PN junction diode does not require any warm up, any heating on its own. The charges, the carriers, those guys that are responsible for conducting current, electricity, they're already there. P-type, N-type. P-type provides the holes, the positive charges. N-type provides the free electrons, the negative charges. So these guys are there ready to move. It doesn't need to be heated. It doesn't need to be warmed like you do to thermionic emission, as in thermionic diode, because thermionic diode makes use of thermionic emission for its operation. You have to heat it up, warm it, so that the filament there will heat up and then electrons will start to move. Thermionic diode makes use of thermionic emission. You know, when you talk about thermionic emission, it is the emission of electron as a result of heating a given metal. Heating, you subject it to heat, thermal energy. Then the electrons will now start moving. So thermionic diode requires warming up, heating it before it will start operating, to start its operation. PN junction diode does not need that. The charges, the carriers are responsible for allowing conductivity. They're already there in the PN junction. And then it is cheaper to manufacture this guy in large quantity compared to thermionic diode. It is cheaper to manufacture this PN junction diode in large quantity than you manufacture thermionic diode. So these are some advantages of PN junction diode to thermionic diode. And this is how we have come to the end of this topic. I want to believe you learned something wonderful from this topic. Chiagozie Andrew, sir, the class is so interesting and educative. I've understood this topic very well now. Thank you very much. I appreciate the commendation, and I am glad that you do understand what we've done in this class. So you can finish what is on the board. We'll take some questions. Let's see the time we've spent so far. This is still 1 hour 48 minutes. Let's see if we can answer some questions before it's 2 hours exactly. Finish up. All right, so I'll be wiping the board. Please, I think I've got to take a screenshot of this also. All right, so I'm going to wipe this. We shall look at 1-2 questions. Frank Donatus. Oh, I just saw your question now. Sir, please, what of inverter? So what's actually your question for asking what of inverter? I don't really know why you ask the question, what do you want to know about it. However, think what inverter does. Inverter converts direct current, that is DC, to AC. So you see, they follow the same principle somehow. Why P-N junction diode converts alternating current to direct current, what inverter does is to convert direct current to alternating current, which is why you make use of inverters at home. All right, once light is gone off and other things, you can make use of the inverter from the solar panel, because the solar panel, once it comes direct current, are you following? The solar panel supply direct current, and then the inverter we convert it, to a form of current, something like alternating current for it to work. So I think one of the major things you should know based on the question you asked about inverter, one thing I want you to know is that an inverter converts direct current to AC current. Is that okay? And like I said, we still make use of this stuff in semiconductor analysis and other things. But this class is focused on P-N junction majorly. But take note that all these inverter, thermistor, transistors, they fall in the same class. And that's why I told you they are non-ohmic materials. They are what? Non-ohmic materials. As we move further in the study of electronics, perhaps in your higher level, as you go, you keep climbing, you will learn more about these guys. Is that okay? You will learn more about them. But for the sake of your exam, please take note that inverter converts direct current to alternating current. Why P-N junction diode converts alternating current to direct current. So let me see, we're going to look at just brief questions. I'll be fast. There's no calculation here, so I think I'll just dictate and then we see if we've been able to cover 1-2 questions as necessary based on this aspect of basic electronics. If what we've covered in the class, can guide you through to answer some basic questions as you might meet in your exam. Definitely, a particular batch must definitely meet questions on this. This one is there. Must definitely meet questions on this. So I've got this particular question here. The major difference, question number 1, Q1. The major difference between a pure semiconductor and a pure metal is that the major difference between a pure semiconductor and a pure metal is that A, the resistance of a metal increases with temperature, while for semiconductors it is the reverse. And of course, that's the answer. I'll still read out option B anyway. Remember, what we're looking at is the major difference between a pure semiconductor and a pure metal is that A, the resistance of a metal increases with temperature. I said it when I was teaching this, that for conductors where you have metals, the resistance is directly proportional to the temperature. But for semiconductors, the resistance is inversely proportional to the temperature, which is what option A said. The resistance of a metal increases with temperature. That is direct relationship. Why for semiconductors it is the reverse. That is, in semiconductor now, opposite is the case. All right, that's resistance of a metal. If it is increasing, the temperature is expected to decrease. B said metals are harder than semiconductors. That's not a major this thing. It's not. C, metals have forbidden gaps, while semiconductors have not. Now, both of them have forbidden gaps. D, why the resistance of metals decrease with temperature. The reverse is the case for semiconductors. Now, why resistance of metals decrease with temperature? Resistance of metal does not decrease with temperature. Rather, the resistance of metals increase with temperature. That with temperature means with increase in temperature. So the correct answer is A, like I said. Let's move on to the next one. Addition of trivalent impurity to a semiconductor. Please, this first question I just gave answer to, we say option A. All right, option A is the correct answer. And what will guide you is remembering that, I think I've said all of those things. Metals, T, directly proportional to R. That is for metals. Then for semiconductors, T, inversely proportional to R. Question number 2. Addition of trivalent impurity. Addition of trivalent impurity to a semiconductor A increases the number of holes. I guess that makes sense to me. If you add a trivalent impurity to a semiconductor is already tetravalent. And I explained to you that in this case of semiconductors, the guy that has more electrons we give, we donate its electron to the other ones. Are you following? In fact, from this thing I said, there are cases that, we have the concept of donor and acceptor. Like in the case of using trivalent impurity. If we introduce trivalent impurity to a semiconductor, the semiconductor will donate electron to that trivalent because the semiconductor has more electrons to give to the trivalent guy that has 3 electrons. They take. Do you understand that, right? So in that case, the semiconductor giving electron to the trivalent impurity will now make that semiconductor to have more holes than electrons. In that case, the semiconductor is a donor, while the trivalent impurity is called an acceptor. Reverse is the case if you are doping with a pentavalent. Using pentavalent, the pentavalent impurity is the donor, and the semiconductor there is the acceptor, because the pentavalent has 5 valence electrons, while semiconductor has 4 valence electrons. So this second question here, addition of trivalent impurity to a semiconductor A increases the number of holes. Yes, it will increase the number of holes on that semiconductor. Remember, your interest is on that semiconductor. What happens to it? B said decreases the number of holes. No. C increases the number of free electrons. No, it does not increase free electron. Remember, the semiconductor will lose electron even, so it reduces the number of free electrons. And then D said decreases the number of free electrons. Decreases the number of free electrons. A and D increases the number of holes. That is A. D said decreases the number of free electrons. I wonder why they will put A and D in this format. This question is somehow, because if you add trivalent impurity to a semiconductor, what will happen? The number of valence electron, which are the free electrons in that semiconductor, will decrease because it will lose electron. And once it loses, the number of holes, we say we have more holes. Okay, well, nothing will happen to the number of holes. Nothing will happen to the number of. If I am seated in exam hall, based on what I taught you, I remember when I drew 2 diagrams here, showing you, okay, let's say originally they have equal number of electrons and holes. When they lose, what is going to happen? So if I am in exam hall, based on these options A and D given, I will go for D, because A and D seem to make sense. But A says that the number of holes will increase, which I feel is expected if you compare the number of holes to the electrons. But hey, what happens there is not as if you increase the number of holes, right? The number of holes will increase, oh. It will increase. Let me draw it on the board and see how the analysis goes. Let me assume I have 1, 2, 3, and 4, and then you dope with a trivalent. If you are doping with a trivalent, so we say you're introducing a trivalent, you know, that trivalent is going to have 3 valence electrons, 1, 2, and then let's say 3. This guy will lose. Already, you know that this we have 1, 2, 3, 4 holes. Yeah, 4 vacant space on its own. In its natural state. So when it loses this guy, okay, let's see, it loses this electron. So this is lost. Let me dot it. What you have here now is hole, because the electron will now enter that trivalent guy. So this becomes a hole. You know our hole, I usually use asterisks. So let us see what happens to this guy. You see, the number of holes increase now. Option A, what did it say? Increase the number of holes, yes. Then option D, let's look at electrons. 1, 2, electrons decreased per se. The electrons decreased. Decreases the number of free electrons. This question doesn't make sense to me. It doesn't. A said increases the number of holes. It doesn't make sense because, yeah, the number of holes increased and the number of electrons decreased. So I will go for A. I'll go for A. Yes, now, that's what I will do. I won't go for D. I'll go for A. From this analysis, that's what I will do. And my reason is simple. You see it clearly that an extra hole has been found. Yes, electron moved, reducing this number of electrons. But we'll have holes. Number of holes will increase. And remember that this thing leads to the formation of P-type. Like I said, this becomes P-type. And I remember saying that in P-type, the majority carrier are the holes. So we have more holes. You see, that is why if you are learning, you want to have the overall view of something so that you will not be thrown off balance by your examiner. Okay, so I'll go for option A. It increases the number of holes. That is why we say that the majority carrier in P-type, where you introduce trivalent impurity to a semiconductor, that the majority carrier there will be holes. So you have more holes there. Although I'm still looking at option D per se, but like I said, if I'm in examination hall, I'm going for A. All right. So that is that. Now I have this next question, number 3. At least let's see if we can answer up to 5. Then we end the class. Which of the following? I hope network has not interfered. Okay, we are still there. Which of the following statements is true about P-type and N-type semiconductors? Which of the following statements is true about P-type and N-type semiconductors? Option A. P-type can be produced from arsenic. P-type can be produced from arsenic. That statement alone is wrong. Arsenic does not produce P-type. Arsenic and antimony produce what? N-type. That's what we learned from our class today. Okay, option A. P-type can be produced from arsenic, while N-type can be produced from silicon. That's completely off. Silicon is not used as a doping material. It's not used as an impurity here. B. Holes are the majority carriers in P-type. I agree with that. That's option B, but we have another part of it. While electrons are the majority carriers in N-type. Good. Option B makes sense. Option B is saying that holes are the majority charge carriers in P-type, which is true. While electrons are the majority charge carriers in N-type, which is also true. So the statement that is true there, I'm going for option B. Let's look at option C and D anyway. Electrons, that's option C now. Electrons are the majority carriers in P-type. No. While holes are the majority charge carriers in N-type. That one is off. D. Electrical resistance of both types of semiconductor increases with temperature rise. Is not true. electrical resistance in semiconductors generally, whether it is pure semiconductors or the ones that have been doped, P&N-Type. Relationship between temperature and resistance is inverse. Is what? Inverse, not direct. But this option D is proposing a direct relationship, saying that electrical resistance of both type of semiconductor increases with temperature rise. So increase in resistance, increase in temperature. No. It doesn't work for semiconductors at all. So the correct option there is B. Holes are majority carriers in P-type, and electrons are majority charge carriers in N-type. Let's move on to the next question. The major difference between metals, semiconductors, and insulators is the issue of A. Ionic bond, B. Covalent bond, C. Band gap, D. Bond well. I take that again. The major difference between metals, semiconductors, and insulators is the issue of A. Ionic bond, B. Covalent bond, C. Band gap, D. Bond well. I am going for C. Question 4. Band gap. Whenever you have a hole formed, that hole is known as a gap. Is that okay? And that is something you see whenever you are dealing with semiconductors. In metals, non-metals, yeah, that band gap stuff, yeah. All right, so I think that is it. That's what I'm going for. All right, we have this next question. What are the charge carriers in semiconductors? Question 5. What are the charge carriers in semiconductors? What are the things that carry charges in semiconductors? For example, in electrolyte, what carries charges there are the ions. So when you come to semiconductors, what carry charges there? They are electrons and holes. They are electrons and what? Holes. And so, where are we? Listen to the options. There are some questions when you are reading it in examination hall. As you read the question, you already know the answer before even looking at the options. Yes. There are things you may know and know very well. Okay, so this question. What are the charge carriers in semiconductors? A. Electrons and holes. And that's the answer. B. Holes only. No. C. Ions and electrons. No. Ions have no business in semiconductors. Under electrolyte, we talk about that. Then D. Ion and holes. The correct answer is A. Electrons and holes. Please, this next question here, number 4. I think my mind is just rewinding around it. Let's see that number 4. The question asks, the major difference between metals, semiconductors, and insulators is the issue of A. Ionic bond, B. Covalent bond, C. Band gap, and D. Bond well. I think band gap, we also have it in the case of metals. Yeah, so that's C. I don't think my mind accepts it anymore. Please, the correct answer there is covalent bond. Yeah, covalent bond. Because semiconductors, they form covalent bond. We know about that in group 4. Right? We know about that in what? In group 4. Now, when you talk about ionic bond, metals do not undergo ionic bond generally. Metals do not. Metals undergo, sorry about that, I retract the statement and repeat. Metals do not undergo covalent bond. Metals undergo ionic bond. Okay? They do not undergo covalent. Metals generally, they are known for electrovalent bonding, that is ionic bonding. We are looking for the major difference between metals, insulators, and semiconductors. Now, option B said covalent bond. Covalent bond. Semiconductors are the only guys that undergo covalent bond. Insulators and what is it called? Insulators and non-metal and metals do not. They do not. Covalent bond. Semiconductors, they undergo it. And semiconductor somehow has this behavior of ionic, because you observe that there is a transfer of electrons forming holes. Now, you know, electrons can move from this atom to a neighboring atom. A total transfer, creating holes. So I feel in that area that there is a nature of ionic bonding there, which means that metals undergo ionic bonding. Semiconductor, there is an ionic character there, even though it is not fully an ionic bonded compound. It's more covalent, but it has that character somehow due to that transfer of electrons, because transfer of electrons is what we know as per ionic bonding, which metals generally undergo, which means you can't really use ionic bonding to differentiate metals from semiconductors fully. But covalent is purely attached to semiconductors. Non-metals usually do not undergo that. So I think I am retracting that option. That question that said the major difference between metals, semiconductors, and insulator is the issue of option B, say covalent bond. That's what I'm going for, please. My analysis makes sense to me as I've given in this second response to that question. So we have 5 questions answered, and what time have we spent so far? So round off. Okay, Emmanuel of 4, you just said something now. So what about the covalent bond? Okay, I think good enough that someone was even making reference to it, but I already gave a response to that. Now, listen to this next question. Let's take this question 6. And that question 6 has this. In a semiconductor junction diode, as the depletion of barrier layer is forward biased, as the depletion of barrier layer, as the depletion or barrier layer rather, not off. I take that question again. In a semiconductor junction diode, as the depletion or barrier layer is forward biased, the layer A widens, B narrows, C remains constant, D widens then narrows. What do we even mean by that? Did our class cover this question at all? And I will say yes to that. Do you remember when I explained the concept of forward bias? At the point I told you what happened in forward bias, P-type of the junction is connected to positive terminal of the cell. N-type of the junction is connected to negative terminal of the cell, creating a repulsion of charges on both sides. Positive charges will be repelled, and then they will flow across that junction. Negative terminals will be negative charges will be repelled. They will flow across that junction. So you see that at that junction, assume this is the junction, you have the holes going this way, you have the electrons coming this way, these holes, and they are crossing this junction. So it's as if they are coming together. They are coming together. Attraction occurs here. This is positive, this is negative. Attraction. And when there is attraction, there is a narrowing of the layer of the gap. Based on this explanation, going back to this question, in a semiconductor junction diode, as the depletion or barrier layer is forward biased, the layer is expected to narrow. Option B says that, gives us that option rather, which is narrow. We are moving on. This next question has this. Silicon doped with aluminium. Silicon doped with aluminium. I did not mention aluminium as a doping material, but of course you have seen it in this question. But did our class cover the concept of having aluminum as a doping material? And I'll answer yes to that. Pay attention as I read this question. Besides, I took my time when I was listing the doping material to tell you something about their valencies. Trivalent, pentavalent. Of course, that answers the question directly, is that not so? Aluminium is in group 3 of the periodic table, hence it is trivalent, which means it will fall or go together with that of indium and boron. The question: silicon doped with aluminium and germanium doped with arsenic becomes, without even reading the option, the answer will be, if you dope silicon with aluminium, aluminium is trivalent, so it will take electron from silicon, making silicon to have less electron and more holes. And when you have more holes in a semiconductor, it becomes p-type. So it's going to cause silicon, that aluminium will make silicon to become p-type. Then you doped germanium with arsenic. Arsenic is pentavalent, so it supplies electron to germanium, making germanium to have more electrons, hence more free electrons than holes. And in that case, the germanium becomes n-type. So the expected answer will be silicon will be p and germanium will be what? N-type. Let's look at the options. A, N-type semiconductors. B, P-type semiconductors. No. C, N and P-type semiconductors respectively. No. N and P-type semiconductors respectively. That's not the answer. Remember, the question was presented in such a way that you have silicon doped with aluminium, that one give you P, and then germanium doped with arsenic, that one give you what? N. Therefore, we are expecting P and N-type semiconductors respectively. Let's look at option D. P and N-types respectively, and that is the correct answer. Question number 7. Let's see if we'll make this up to 10. D is the correct answer. P and N-types respectively will be found. Next question, number 8. When impurities are added to semiconductors, the conductivity of the semiconductor, I take that again. When impurities are added to semiconductors, the conductivity of the semiconductor A remains constant, B increases then decreases, C increases, D decreases. Pure semiconductor has high conductivity value. Pure semiconductors. When you add the impurities to get all these P-type and N-type, it reduces their conductivity. Are you following, right? It reduces their what? Conductivity. Yes. See, now you are putting impurity. Something has happened. And sometimes excess of the electron will be given. Other times, electrons will be stolen away. So it will reduce the effectiveness in terms of conductivity of that material. Does that make sense? So the correct option is D. When impurities are added to semiconductors, the conductivity of the semiconductor A remains constant, B increases then decreases, C increases, D decreases. That's the correct answer. The correct answer is decreases. Next question. The bond between silicon and germanium is A, dative, B, covalent, C, trivalent, D, ionic. The correct answer will be covalent. That's the bond between them. Question 9. That's option B. Okay, so I think we want to take the last one, number 10. Question 10. And then we'll have this simple one here. We'll have this simple one. The question reads, I will give you the way the thing is presented here, right? I we have small size, I, low power requirement, I, not easily damaged by high temperature, not easily damaged by high temperature, then IV, highly durable. So these parameters were given. These parameters there were given. And we have this question. Which of the above are advantages of semiconductors? Which of the above are advantages of semiconductors? And looking at this small size, remember when I talked about PN junction diode, I mean the advantage over thermionic. I told you something about small size, so that one is an advantage of semiconductors generally. Low power requirements, yes, an advantage. Remember I told you then that if you compare perhaps the PN junction diode with thermionic diode, the PN junction requires a smaller, all right, lower potential difference to operate it than that of thermionic. So in the case where we say that the PN junction semiconductor type of semiconductor PN junction diode as a type of semiconductor, that the potential difference you apply there is small compared to the other. If potential difference is small, then we expect power to be small because power is equal to IV, current times the potential difference. So this is an advantage also. Then we have not easily damaged by high temperature. Yes, not easily damaged, because you know that for semiconductor, the higher the temperature, the higher the conductivity. In fact, it is expected that the temperature should be high. So that III is also an advantage. Then IV, highly durable. Yes, it is highly durable. That is why it is easy to carry it along. Something that is small, use it, it works for you, and you know, can carry it along. So it lasts better. Semiconductor, yeah, it lasts better, you know, and these are advantages. So I think all of these given here, the advantages of semiconductors. Option A, I and I only. Option B, I, IV only. Option C, I and IV only. Option D, I and IV. Option D is the correct answer. You know, this kind of questions, all right, this kind of question where they will list parameters and then they want you to select which is correct. So D is the correct option. All four parameters provided are advantages of semiconductors. All right, guys, it's been a wonderful class with you, and I hope you learned something great from this particular semiconductor class. Please remember to share these video lessons to your friends. Okay, anybody you know who is sitting for this jam and WAEC, make sure you share this video to the person. Encourage the person. You are now learning from the comfort of your home, where GMAETS 41 is making this learning fun, easy, homely, and targeted. I know that some of you might be complaining and talking about data and this and that. Hey, remember, you're a student. You want to sacrifice all that is necessary for your studies. Look at me now. I'm streaming from this device to check what is happening at that end. Are you getting me right? In case network disturbs and other things. and I'm still using data to run the camera. So you can just imagine what I am burning as data. So that will make you to work hard. Know that it's not just only you, okay? And you are doing this for a reason, to make sure you get the best in your studies. Do you understand that? So that shouldn't be your worry. It shouldn't. Make sure you're always available, connected to this class, and you will get the best, okay? I will be releasing a short video on chemistry, but that's going to be a pre-recorded video as it is. So you can visit the chemistry playlist. The video will be uploaded tonight. Okay, visit the playlist. It's going to be on something about chlorine. I'd like you to know something about chlorine, preparation of chlorine and stuff like that. So I'll be seeing you tomorrow. God willing, we are going to take on maths. We're going to take on maths tomorrow. And of course, I'll be holding a class on the GMAETS 41's basic class channel. Is that okay? I'm going to host a class there. And more information will come on how tomorrow's class is going to be, because I'll be taking another subject, not only maths on this channel. I'll take another subject on this channel as well too. So stick around and stay connected, so that once I kick off the class and or I upload any video lesson, you will be personally notified. Don't forget, like I said, I hope you are benefiting a lot from this channel. You can support GMAETS 41 by sending a super chat, super sticker. You can also become a channel member. That makes more sense. If you're becoming a channel member, just click on the join tab below the GMAETS 41's video lesson once you are taking any lesson, or you go to our homepage on this channel. You will see the join tab. Click on it. Then you can join from the platinum level to the diamond level. That is a monthly support. Okay, the platinum level is 2,000 naira monthly. So you see, it's something that is very much considerate, and so I really appreciate that. Okay, thank you, and do have a wonderful night rest. Very importantly, don't forget to share this lesson and many other videos on this channel. Let us build this channel together. Let us build it together. Can we target 10K subscribers? We are at 6,000 and something subscribers now. Can we target 10K subscribers, given a limit of, even if it is within 1 to 2 months, right? Let's keep moving. I'm not expecting anything magical, but I know that with you and by the support that GMAETS 41 receives from our God and Helper Jehovah, that we can push this channel further so that many more people will benefit. I've always expressed my love for all of you, and it still remains. Good night.